Swayam Prabha. Digital India. Educated India.
So we can continue discussing how to make ceramics using components using additive manufacturing of soil gel formulations. And since the alkoxides contain oxygen, of course, it is easy to obtain oxide ceramics with them. But we can also exploit carbothermal reduction reactions and use a carbon source as a way of eliminating oxygen from the structure, and therefore obtain carbides, for instance. And what I'm discussing is a different approach for making non-oxide ceramics. And this is in the framework of a project that we have been running for several years with the Italian nuclear physics laboratories. There is a series of laboratories, one of them is located just outside Padova. And in this laboratory, they have acquired funding, 18 million euros for a very significant project for the fabrication of, for the generation of radioactive beams. And the process works in this way. You have a cyclotron that provides protons, and then you have a target that gets hit by the protons, and inside the target you develop isotopes depending on the composition of the target. And then you need to extract these isotopes that have a very short lifetime often. You ionize them, and then you separate them by mass, and in this way you can obtain a single type of radioactive beam. And then with the radioactive beam, you can do radiopharmaceuticals production for diagnosis and therapy, or you can simply do nuclear physics studies. So we have been involved with the fabrication of the production target. And the requirements are very strict. In order to facilitate the extraction of the isotopes, the material operates at very high temperatures in high vacuum, meaning 2000 degrees, 10 to the -9 torr. So very demanding conditions for any type of materials. Carbides are fine, mostly fine for this type of environment, and you select the correct, by changing the type of carbide or metal in the carbide, you change the type of isotope that you can generate. And in order to facilitate the extraction of the isotopes, the process is called not diffusion, but it's called effusion. This is facilitated by two things. One, the presence of additional carbon. So we should not make stoichiometric carbides, but carbon-rich carbides, because the isotopes released from the carbide grains tend to exit the material more easily if they can run through a percolating carbon structure. And the presence of porosity helps with the effusion, with the release of the isotope, which are then extracted and further processed. So ideally, we need to have stable micro and meso porosity, which is of course difficult to retain at 2000 degrees for a long time. And besides that, we need macro porosity also in order to have a better handling of thermal temperature differences thermal issues, and in order to have, again, a more facilitated extraction, a more simple extraction of the isotopes. So we used, and in the beginning, we used foaming as a way of making a component with the required characteristics. And then we switched to additive manufacturing with the obvious advantages that you can also generate, for instance, gradient porosity structures that would have enhanced behavior from this point of view. So this is the project, and we worked on titanium carbide. In the past, we worked also on lanthanum carbide as a substitute, non-radioactive substitute of uranium carbide. And our student also spent some time in Germany at a facility that could handle uranium precursors. So titanium carbide is the material choice for one specific type of isotope that they want to generate. And by the way, the system is now running. They're not yet using our targets. They're using commercially available silicon carbide discs that have some limitations in terms of the ability of release the isotopes, but they wanted us to do titanium carbide. And you can buy titanium carbide powders. You can make discs that are required as target. The target is actually comprised of a series of discs, seven discs of this size, and the thickness is about 1 centimeter. And the problem with the titanium carbide is that after sintering, you have a dense material. It's very difficult to achieve a high specific surface area, which of course would indicate the presence of micro and mesopores. Also, by using titanium carbide powders, we were not able to use DLP because titanium carbide powders absorb and scatter the radiation, and therefore you cannot, they are not printable. So we switched to sol gel synthesis of carbides so that we could use DLP with higher geometric flexibility and the possibility of generating in situ some mesoporosity. So we can start from titanium isopropoxide. With the carbon source, we used sucrose, and then we added a chelating agent, which simply served acetic acid, which simply served the purpose of controlling the reactivity of the titanium isopropoxide and extend the lifetime of the solution. And after preparing the material, we, in this case, we simply created powders, and because we wanted to have a look at the material by itself, and we generated titanium carbon nanocomposite structures with a titanium over carbon ratio of 1:5. So we were quite over stoichiometric in terms of carbon, and the graphitic carbon generated thin sheets at the grain boundaries of titanium nano-sized crystals with a size of about 22 nanometers. And at 1750 degrees in vacuum, you have the carbon-thermal reduction reactions. You lose all the oxygen, generating the carbide, and the material at the end had a very high porosity in terms of micro and mesopores, and especially micropores, and that is why the material had a very high specific surface area. So we started from this formulation, and we had to make it photocurable. And in order to make photocurable, then we added the photopolymer. For instance, we added PEGDA, which is a suitable material for this. And again, we generated a sol gel network and a photopolymer network. And in this way, we were able to achieve the fabrication of structures with complex shapes. This is just one example, and this is not in the form of a disk. We wanted simply to be able to generate structures and then check if the structure could be effectively converted to a titanium carbide structure without losing the shape. And you can see that after carbothermal reduction reactions, we were able to retain the shapes. Here you can see different structures. This is a diamond structure, and this is a Kelvin cell structure. This is another type of structure, all based on struts. Of course, we can also make structures based on sheets rather than filaments. And we had a significant shrinkage due to the fact that we were using a sol gel formulation. So this type of material, after sintering in 1750, had a limited amount of residual porosity, and therefore a limited specific surface area. And we wanted to increase that. So we collaborated with a researcher from Hebrew University in Jerusalem, who is an expert in sol gel materials, and especially in mesoporous and microporous sol gel materials. So we used a self-assembly approach using a templating agent in order to generate a material that, after gelling and removal of the template, would allow us to obtain a mesoporous material. Another possibility for introducing meso and micropores is to do supercritical drying. I don't know if you're familiar with aerogels. Aerogels are components that are obtained by evaporating the liquids inside a gel obtained from sol gel chemistry, but using supercritical drying. And in this way, you avoid the capillary tensions that would lead to cracking of the gel and densification. And therefore, you obtain a highly porous material after this supercritical drying. So we tried first self-assembly, then we tried supercritical drying, and then we proceeded to have combine the two. So you have your sol gel that is precursors are hydrolyzed, they start condensation, and then you obtain either what is called a zero gel after ambient drying, or you obtain an aerogel after supercritical drying. After firing, we obtain titanium carbide nanocrystals plus nanocrystalline graphite with excess carbon as desired. And you can see there the different size for the crystallites, which is always the same because it doesn't depend, of course, on the fabrication route. The material is the same. And you can see also the Raman information on the graphite. If you look at the microstructure of the material, you can see that you have titanium nanocrystallites that are randomly oriented in a carbon matrix and surrounded by graphene layers that derive from the turbostratic graphite distributed along a specific plane for the lattice. And with this type of textural control that we carried out. You can see that if you do not do any type of microstructural control in terms of the porosity, so if you simply have the zero gel, the specific surface area is not very high. If you do the templating or you do aerogel, you obtain almost threefold increase in the amount of specific surface area. And if you combine the two, you get an even higher amount of specific surface area. And note that the volume of micropores decreases is changed by modifying the fabrication approach. And if you look at the BET curves, you can see, for instance, that the aerogel plus template approach has some distinct presence of mesopores inside the structure, plus the micropores that contribute the most to the specific surface area. For our application, having mesopores, so between 2 and 50 nanometers, is favorable for the release of the isotopes. So this is a good material that we were able to develop for this specific application. And the next question was if this material could endure working under extreme operating conditions. So we didn't go to 2000 degrees, 10 to the minus 9 millibar. We went to 17 and 1800 for 24 hours at 10 to the minus 6 millibars. And we observed the progressive loss of titanium with decreasing temperature, which means that probably we need to operate the system at a lower temperature, which is certainly feasible. It will reduce the effusivity of the isotopes, but at least the material will not be damaged. And this problem of the release of titanium comes from the material itself, but possibly also due to the nanostructure and the presence of micromesopores that facilitate that increase the specific surface area, increase therefore the geometric surface area exposed to the high vacuum conditions. So nevertheless, the samples maintained the structural integrity and retained at least some degree of textural properties. You can see the test carried out on the aerogel, and the reference was had 328 square meters per gram. After 24 hours at 1700, you have the release of the loss of 1/3 of the pores, of course, due to sintering, but you're still left with some mesopores. So this means that not only you need to be mindful of the temperature which you operate, but also of the time at which the material is exposed to the environment. For the applications we are looking at, this is still suitable. It means that we need to substitute the target after a certain amount of time. And for the aerogel, we also had a similar behavior. You can see the change also in the pores, and basically you reduce the micropores, and that's why you're reducing the specific surface area. We tried also, we were interested also in manufacturing uranium carbide targets for the same application. And in Germany, the student was able to use a precursor for uranium, and she used the modified Pacini synthesis to have a molecular level homogeneity of the precursor within the structure of the material, and after pyrolysis, the printed material retained the shape and the structure, and they've not been able to do any BT because they don't have a BT that can do work with radioactive materials. But you can see that they were able to run XRD measurements on the hot material, and you can see that after 24 hours at 1700, they had a complete conversion of the uranyl precursor into uranium carbide with a lot of additional graphite, which is what they wanted. And two different phases of uranium carbide formed. Very large volume shrinkage, but that's not a problem because, as I've shown here, the sample maintained the integrity and there was no cracking in the material. So in conclusion for this part concerning the sol gel fabrication, I can say that you can use sol gel formulations for making oxides. We were interested specifically to fabricate silica glass. Again, if you try to obtain silica glass from sintering or particles, you will not be able to obtain transparent materials unless you use colloidal silica. But if you use colloidal silica, then you will not be able to dope that with an alkoxide to increase the refractive index, because you will obtain a crystalline material which is non-transparent. If you process in an atmosphere with a carbon source, then you can make carbides. And I forgot to mention one thing concerning the silica zirconia system. If you're familiar with zirconia, you know that it crystallizes. And in fact, the silica zirconia system is actually a glass ceramic, but because there are tetragonal zirconia crystals, but the size of the crystals is about 3 to 4 nanometers, and therefore the material is fully transparent. So I have now a part that I would like to present on additive manufacturing of geopolymers. So I would like to continue the discussion of making components from additive manufacturing of precursors. Okay, so this part is related to additive manufacturing with geopolymers. The rationale behind it is that we are interested in making components that have specific properties, and I hope that I will demonstrate to you that geopolymers are an interesting class of materials that can be used for a large variety of applications. So what are geopolymers? I don't know if you're familiar with this class of materials. I know that one of you told me that he's working with geopolymers, so I'm happy that someone is conversant with this type of topic. So basically, well, first of all, the name geopolymers doesn't mean anything. It was given by a guy, Dr. Davidovits, a French scientist, who came up with this idea, but his background was polymers, and he called these materials geopolymers because, as you will see, they have a structure that is similar to the structure of a reticulated polymer, and they form by condensation reactions, meaning that in one sense they polymerize. And they call them gel, because of course they are inorganic. But to a glass scientist, if you look, I will show you the structure of the geopolymer, you will recognize that it is simply the structure of a glass. So the term geopolymer really doesn't make much sense from the point of view of a person working with ceramics. So in any case, they are based on a chain or network of mineral molecules. So everything is inorganic. And these mineral molecules contain as a network forming agents, silicon and aluminum. And in some cases, these networks can be based also on iron oxide species. And then you have some balancing cations such as sodium, potassium, in some cases, magnesium and calcium. So these materials are based on a continuous network, three-dimensional network with covalent bonds within a variable microstructure. And let's forget a little bit about the ion-based geopolymers and consider just the, let's say, regular geopolymers based on aluminum and silicon species. They are obtained quite easily and readily at room temperature by the interaction between a highly alkaline solution and a reactive form of aluminosilicate. And a typical reactive form of aluminosilicate is metakaolin, which is, of course, simply the decomposition product of kaolinite. If you take kaolinite and you heat treat it to, let's say, 700 to 800 degrees, you are at a temperature too low to start forming mullite and liquid phase, but you decompose completely the structure of the clay, and you dehydrate the clay, leaving a material which is amorphous and highly reactive. And if you put this aluminosilicate source into contact with a highly alkaline solution, by highly alkaline, I mean pH 13, 14, then you have a very ready, quick, and complete dissolution of the metakaolin, of the solid metakaolin particles. The size of the metakaolin is typical, a few microns it's platelet-like, like 6 microns in length, and maybe a few nanometers in width. So these platelets dissolve very, very quickly and completely and effectively in a highly alkaline environment. One interesting feature of geopolymers is that you do not need to start from a clay to obtain a highly reactive aluminosilicate material. For instance, you can use fly ash coming from coke plants, from electricity plants using coke. You can use other sources coming from waste that contain aluminum and silicon, like metallurgical slags, which are reactive because they are amorphous. So one of the specific features of geopolymers is that they can be obtained from cheap raw materials. 1 kilogram of geopolymer, we computed that it costs, starting from metakaolin, which is a, let's say, expensive product with respect to a waste product, costs only about between 1 and 2 euros to make. So inside the structures, inside the structure of the geopolymers, you have tetrahedra of silica, you have octahedra of alumina, and then you have a combination of the two. And you know from glass science that aluminum oxide is 6-fold coordinated. Therefore, it is not a network former, but a network modifier. But if you have stabilizing cations, so if you have enough sodium or potassium ions to balance the lack of the fourth cation for the aluminum ion, then you can stabilize the aluminum into tetrahedral coordination rather than octahedral coordination. And in this way, aluminum becomes a network former for a glass, and you form a continuous three-dimensional network where you have only bridging oxygen bonds, and around attached to or around close to each aluminum ion, you have a balancing alkaline cation. So the structure, you can understand why the original person working on this field, called this a polymer, because you have this the formation of this continuous network, reticulated network. But again, as a glass scientist or ceramist, you can recognize that this is simply a aluminosilicate glass structure. There's one interesting point to make. So you have this highly reactive aluminosilicate source, and you can react it with an alkaline medium, just as I explained you now. And the alkaline medium is typically based on sodium hydroxide, a combination of sodium hydroxide and sodium silicate. But you can also react it in an acidic medium. And in this way, you obtain a different class of materials. You obtain phosphorus-based materials, or phosphorus-containing materials. So if we look at the geopolymerization of metakaolin, this goes through different steps. First, you have the alkalinization, formation of tetravalent aluminum in the side group silate, and this is stabilized by the presence of the alkaline cation. Then you have the attachment of the OH base to the silicon atom, and then you start the dissolution of the silica network. You have the cleavage of the siloxane oxygen through this electron transfer mechanism from silicon to oxygen, and then you form hydroxide species. And then you keep creating hydroxide species, both based on silicon and based on aluminum. So after, and then you have finally the reaction of the SiO broken bond with the sodium cation, forming termination bond. You can also have this besides forming OH groups. So this occurs spontaneously, occurs quickly, and by quickly I mean in the order of a few minutes at room temperature. Of course, you can use the temperature as a driver for speeding up or reducing the speed of these reactions. And the main point is that after the dissolution of the reactive aluminosilicate, you have a solution that contains hydrated species in an alkaline environment. And what they do is that they start condensation reactions with release of water. And therefore, you start forming silicon-oxygen-silicon bridging bonds, or silicon-oxygen-aluminum bridging bonds. And by doing that, you basically polymerize the species in the liquid, and you start forming a solid. So the material becomes a solid. So you have your aluminosilicate source, you have dissolution, and then you have precipitation or formation of a continuous three-dimensional network. And this three-dimensional network is not just continuous, but it has a lot of interesting characteristics. Before going into the microstructure, and I'm talking about this because in this way you can understand why we are interested in using geopolymers for a wide range of applications. So I told you that you have a reactive aluminosilicate source, and then you add alkaline species, including sodium silicate, which means that depending on the formulation of the starting materials, you can have different silicon to aluminum ratio. And according to Dr. Davidowitz, who leads the Institut Geopolymer in France, depending on the type of, or depending on the composition, you end up with different type of three-dimensional structures in your material, and depending on the structure, you can achieve different properties for your material. So if you have a low silicon to aluminum ratio, you obtain a very rigid 3D network that can be used for applications, the applications that you see there. So before talking about the microstructure of what is formed, let me make a comment. So basically, this is like a cement, okay? So you take your material, dry powder, you mix it with a liquid, and then you have reactions, and you form a solid. And similarly to the cement, the volume occupied by the solution is similar to the volume occupied by the solid, which is, of course, a very non-trivial but a very important point. So you have very limited shrinkage. So one could say, well, why are you interested in such a material in a cement? Well, the reason is that there is a very strong difference between the structure of a consolidated geopolymer and the structure of, let's say, consolidated Portland cement. In hardened Portland cement, you're familiar with the fact that the solid is held together by secondary bonds, because you form hydrated species in the form of nano-sized viscous crystals, or not real crystals, but viscous, and with a composition similar to that of tobermarite. And it is the secondary van der Waals and hydrogen bonding between these solid components that lead to the strength of the material. And the problem with these hydrated species is that they are not fire resistant. As soon as you dehydrate hardened Portland cement, you lose the strength, because the strength is given by these secondary bonds. In geopolymers, you have the same benefits of being able to consolidate a fully inorganic system at room temperature, but this material can withstand high temperature. And so this is extremely meaningful for a wide range of applications. Today, I will be talking only about, not today, because I think we are almost finished. I will be discussing additive manufacturing of geopolymers. I'm not discussing other things that we do with geopolymers, but if you can think of a binder system, for instance, a lot of people use phenolic resin as a binder, and phenolic resin works fine, but it is expensive, smelly when you make it, and so forth. We have been substituting, for instance, phenolic resin with geopolymers for making brake pads for cars. And we have been working for 10 years with the company, and we have several patents on that. And the advantage of having a fully inorganic system with respect to an organic binder is, of course, much higher thermal stability. So anything that has been made using polymers as a binder or as a matrix could be substituted with an inorganic binder. And if it is a geopolymer, it can withstand high temperatures. Of course, the component will have different properties, so not everything can be substituted. For instance, we're making composites and the matrix. So we are using carbon fibers, or we're using glass fibers to reinforce a geopolymer matrix to substitute polymer composites that are not load-bearing components. Because, of course, the geopolymer matrix, being inorganic, does not have the same properties of an organic matrix. And from the mechanical point of view, it's much worse. But there is a wide range of parts that are made using plastic forming technologies and polymer matrices, simply because it is convenient and reasonably cheap. But then you have, for instance, fire hazards that are problematic. So, for instance, in a train, in a car, there are components made of plastic composites that could be substituted. They are non-load bearing and could be substituted with an inorganic polymer. Of course, the density is higher because the density of these geopolymer is around 1.8. So you have to take that into account, but maybe you can reduce the thickness of the component. So I'm saying this now just to make you understand that this is not just an inorganic binder, but it's a system that has a lot of potential for high temperature applications. And effectively, in reality, we can look at what happens when you heat up your geopolymer, and this heating up could happen during use, or you can do it before. Personally, most of the applications we are looking at use geopolymers in the as received state, for the reason that I will explain in a moment. But anyway, if you take the a geopolymer block and you start heating it up, it doesn't disgregate like it would happen for Portland cement. It simply becomes a dense ceramic. And for sodium system above 800 degrees, you start crystallizing nepheline, which is a sodium silicate. It's a ceramic material with the problem that the melting temperature, if I remember correctly, is 1040, something like that, Celsius. But if you use potassium-based geopolymers, then you start forming lucite, which is potassium silicate with a melting temperature of 1680. So you can obtain high temperature resistant materials. Some people in China, for instance, use cesium-based materials. And in that case, you make a ceramic phase called pollucite that has a melting temperature of 1950, if I remember correctly. And the reason for doing this is that you have all the advantages of forming a component from a liquid, from a suspension, and consolidating at room temperature. So you don't need to sinter powders, okay? And one interesting point is that these materials have a composition similar to some zeolites. So people say that these materials are cryptozeolitic because at room temperature you don't have fully blown zeolite crystals, but you can obtain for certain compositions certain zeolites without hydrothermal treatment. Here is the example for forming lucite at above 1200 Celsius. You have phase pure lucite. If you have your hardened material at room temperature, it is amorphous, remains amorphous up to intermediate temperatures below, let's say, 800 degrees. And above that, you start forming crystals. So some of the, I already mentioned some of the positive features of geopolymers. One is that they do not emit CO2 during production. I mean, you have to go through the decomposition of the kaolinite, but you can also use waste materials. And if you use waste materials, then that's more favorable from the point of view of CO2 emissions. And what you obtain is a gel-like structure that is based, since you are carrying out condensation in alkaline environments, similarly to, if you wish, solid gel systems, you obtain amorphous aluminosilicate particles that are bonded together. And this leads to intrinsic mesoporosity. And the fact that the porosity is meso means that the typical specific surface area values is not very values are not very high, but we can control that and increase the amount of specific surface area up to almost 200 square meters per gram. And for a lot of applications, having a micro mesoporous material is very, very useful, because this is interconnected porosity that gives you high capillarity, high water and gas absorption ability. So geopolymers have been proposed for evaporative cooling, for catalysis, for gas absorption, water purification, drug delivery. So that's why we are interested in additive manufacturing of geopolymers, because we can start from cheap raw materials. We can control the rheology of the system. We can obtain shapes that can allow for high permeability. And we have a material that can be active towards certain needs. For instance, water purification. The geopolymer can ion exchange alkaline ions for heavy metal ions that are present inside the water. So for instance, geopolymers are very good for absorbing arsenic, for absorbing lead ions from water. So we're interested in manufacturing porous geopolymers, and the reasons are listed here. They come from cheap and low sustainable and sustainable raw materials. They consolidate at room temperature with fast setting reactions. You have a gel structure, and at the beginning of the forming of the network, you have a reversible gel. So if you apply a stress, for instance, because you want to extrude, you break easily the bonds of the gel. And when you stop the stress, because the paste has come out from the nozzle, the gel reforms, forms back again, and you consolidate the material without losing the shape. And the mesoporous structure provides this interconnected permeable network, and the amount of mesoporosity is about 40 volume%. So in a solid block of geopolymer, you have 40 volume% of mesoporosity. And this is the structure of the geopolymer. You see the fourfold coordinated aluminum cation that is ion that is stabilized by the alkaline cation. And this can be ion exchanged in solution. And we have been working for geopolymers for quite a while. We started making foams, then we started making granules, and then we now are making lattices and other structures that I will show you in the next lecture.
So I have some
Yes.
like on the solder method, the titanium carbide. Like
yes,
the reason that you want to do solder of titanium carbide is not possible to make any porous titanium carbide through the conventional tool.
Yes, so it's twofold. The reason why we switched to solder solutions. The first one is that we want to make complex shapes, and directing writing has some limitations in terms of the type of shapes that you can generate. And the second point is that fact that we want to embed micro-mesopores in the system.
Because I thought of adding some fillers that can, like campaign or something, that will burn on your high temperature, so we can get some porous structures.
Yes,
the
but
complex shapes may not be what.
yes, but also, I mean, with camphene, I'm not sure you can obtain micropores, and I'm not sure what is the volume of the porosity that you'll be able to create. If you start from molecular precursors and you go through carboth-thermal reduction reactions, it's much easier. Yeah.
Did you try any other carbides by this?
So we published on boron carbide. We've done lanthanum carbide, but we have not done additive manufacturing of those.
Coming to the lanthanum carbide, is it stable in air?
It's moisture sensitive.
Yeah, it's more.
Yeah.
Process after condensation, there was two process. One was extrusion and then aeration.
Yes.
So this process, like, what is the probability of cracks or something? Because
Yes. So the sol gel process works very well for low dimensional objects. So for coatings, but for instance, for coatings, if you go above, let's say, 0.5 micron, you start getting cracks, drying cracks. Okay. So it is very, very difficult to obtain a component out of a zeogel. And that is why aerogel or supercritical drying was applied, because in that way you can obtain the dried component without cracking.